Great. Well, welcome everyone. Happy to have Bo Peng at this week's electronic structure discussion group. And without further ado, I'll turn it over to you. Thanks, Bo.
Okay, thanks for coming to my talk. So I'll talk about non-abelian braiding of phonons in layer silicates. I'll first start from some basic concept of non-abelian braiding and how we extend this idea into the braiding of momentum space. In particular, we show a material family layer silicate, which is earthly abundant in clays and soils, and they're literally everywhere. And we show the phonons of this material can realize this non-abelian braiding. And the last thing is we show that we can use Raman spectrum to do as an experimental signature to detect this non-abelian process. We'll start from some big pictures. So we know that conventional computers use 0 and 1 as a bit to do the calculations. And instead, the quantum computer, they use a quantum bit. So because of this quantum entanglement and superposition, a qubit can both be 0 and 1 at the same time, and 50 qubits can be the classical computer. And 2 years ago, actually, Google claimed that it achieved quantum supremacy, and with 53 qubits, it can finish a calculation in 200 seconds, where conventional supercomputers take more than 10,000 years. There's also other proposals because we know Google used superconductivity as the quantum computer. And here are also other proposals based on this topological qubit, because we know that because they are topologically protected, so that means they are immune from the environmental perturbations. And so, for example, they use this non-abelian anion to do this topological qubit. For example, if you're winding an anion around the other anion, this is topologically distinct from the lower case, which is not around the other node. This proposal, based on this quantum information, based on this kind of non-abelian braiding process, we can encode quantum information in this braiding, and as long as the braiding process is correct, the quantum information is immune from the environmental perturbations. And the thing is, how do we realize this non-abelian anions? So because we know that anions are not bosons or fermions, and there's something in between, and their exchange are quite different from these conventional particles. So one of the most famous proposal is actually based on this Majorana zero mode, and in a material called topological superconductor, basically you can place a semiconductor nanowire on top of the superconductor. And so you can realize this Majorana zero mode in real space. The thing is, this proposal is kind of the disadvantage of this proposal is that it's hard to build and detect this Majorana zero mode. So for example, this year, there's Nature just retracted a paper from a Microsoft lab team saying they realized the quantized Majorana zero mode. So can we go beyond this kind of traditional proposal and propose something new to realize this non-abelian braiding of quasi-particles? One of the alternative approach is actually based on the braiding momentum space rather than the real space. So to realize this braiding in momentum space, we first will need the band nodes, and we know that band nodes are kind of band crossing point in the momentum space. And the other requirement is that these band nodes must carry the non-abelian charge. And we'll analyze how do we realize these two requirements. So first is the band node. This is quite simple because it can originate back to the paper of Phonons 90 years ago. This is this basically saying on what condition the band can cross with each other. So for example, if we take a diatomic system as an example, if these two atoms are separated from each other, they only have isolated energy levels. And if we put these two atoms together, the atomic orbitals will hybridize with each other, and there will be some band crossing points. The thing is, in general, these band crossing points tend to hybridize with each other and be gapped, and only under some symmetry constraint that this band crossing will be protected. So for example, if we consider a 2 by 2 Hamiltonian, because we are only interested in the band crossing point, we can only consider 2 by 2 Hamiltonian. This Hamiltonian have the same eigenvalue with the same like tuning parameter of the distance between atoms. That means the matrix must be 0. To fulfill this matrix, we need this diagonal term to be equal to each other and off diagonal term to be 0. Now we have only one tuning parameter, that's the distance between two atoms, but we have two equations to solve, which means this kind of two equations are not solvable unless one of these equations can be automatically satisfied. For example, if the two bands have two different irreducible representations, the second term will automatically be satisfied. So we'll only have one tuning parameter with one equation. So only under these two bands belong to two different eras, we can get band crossing point. This, for example, if we take a mirror symmetry as a condition, and for mirror symmetry on the mirror plane, we can use the mirror eigenvalue to label the bands. And for the left case, the two bands have the same eigenvalue and they will be hybridized with each other and gapped. And for the second case, the two bands have two different eigenvalues, so their crossing will be protected by symmetry. As we mentioned before, they belong to two different eras. So we can solve this Hamiltonian, and they cannot be hybridized with each other and gapped. Although this proposal was actually proposed like nearly 90 years ago and extended to energy band of crystals shortly after, not until recently or recent decades until people realized that these band crossing points are actually associated with certain topological environments. For example, in YSM metal, we can associate a Chen number with these wire nodes. Basically, we do a manifold, spherical manifold around the band crossing point, and this can give us opposite Chen number for different wire points. For example, -1 or +1. And so this is basically a band node. But to realize a braiding, we also need these band nodes to carry a non-abelian charge. So this is more complicated because for the band nodes, we only need two bands. But to carry the non-abelian charge, we need some mathematical form, which is more complicated than just a two-band crossing with each other. So basically, we need two requirements. The first is we need C2T or PT symmetry. That means the Hamiltonian can be real. And this gave us the real eigenvector, so we can play with. The other thing is we need more than two bands. So different from a single node, we now need at least three bands. For example, here we can label like -1 or I as a first gap, and then -J and J as a second gap. So the thing is, we can use some mathematical calculations to think like this kind of nodes are actually related to the frame charge. I mean, this frame charge associated with this node are quaternion values. So we can label this I and J, they belong to the quaternion group. And this quaternion group form a non-abelian group. That means they do not commute in the adjacent, in the neighboring bands. So we can get some non-abelian charge carried by these band nodes, as long as we can have this symmetry, and at the same time we have more than two bands, we can fulfill this non-abelian charge. Let's take an example of how we realize this non-abelian braiding by playing with the position of these band nodes in the momentum space. So we'll first consider the first case that we only have. We use this open and filled triangle or circle to denote like minus or plus the sign of this node. And for the first case, we have this -I and I in the same gap, or -J and J in the same gap. So that gave us a topological environment called Euler class, and this Euler class is 0. That means this I and -I can annihilate with each other. However, if we do some momentum space braiding, saying we let this open triangle around this open circle, so basically that means we need this node to do some winding around the other nodes in the neighboring gap. We can give a Euler class of 1. So we now get two nodes with the same frame charge of I, and they cannot be annihilated with each other. So this braiding give us a different Euler class, and this Euler class is the topological invariant. We define this non-abelian charge. This can be summarized in this figure. For example, we can just use the adjacent nodes and principal nodes, which means we have more than two bands. And we can winding these nodes in the momentum space. And as long as we can realize similar braiding process, we can either get the Euler patch of 0 or Euler patch of 1. And we can only unbraiding this process by reverse the time. So basically, this is a function of time, and we can realize this non-abelian braiding in the momentum space. So far, these proposals have only been realized in the electronic systems, and for the electronic systems, they're only like theoretical predictions. And recently, there's a paper using artificial systems and use some pump probe experimental way to verify this non-abelian braiding. So the thing is, can we find some more material candidates? Because so far, these materials are limited in electronic systems. So our proposal is actually based on phonons. We know that phonons are atomic vibrations and they're intrinsic properties of solids. So basically, they're everywhere. And we can use Raman spectrum or some inelastic neutron scattering to measure these phonons. One of the most fascinating things about phonons is their bosonic excitation. So unlike the electronic systems, they do not have the restriction of Fermi-Dirac distribution. So for electronic systems, these three bands and band nodes must near the Fermi level. If the Fermi level are too high or too low than this band crossing point, it is hard for the experimentalists to verify them. And we also know that all these transport properties are related to the electronic states near the Fermi level. So if they are too far away, we just can't know any contributions from these nodes. And the other disadvantage of electronic systems is electrons. They also have spin-after coupling, and that means it might easily to break this time reversal symmetry, for example, by an external magnetic field. But for phonons, they are charge neutral and they are the kind of spinless systems. So they are immune from any like magnetic field. It's not actually actually compared with the electronic system, we know that they are kind of well studied in single gap system or single gap topology. In this multi-gap systems, for example, we need more than 2 bands to study this band crossing point. Phonons may be a better choice, better candidates to study this non-abelian features, because for electrons, we need to detect this kind of non-abelian process around the Fermi level at the same time, and we also need there's no time reversal symmetry. So basically, to realize this C2T symmetry requirements. So our candidate is actually an earthly abundant material called Kagome silicates, and they can form a monolayer. And the oxygen there's a silicon oxygen tetrahedral around these silicon atoms, and these oxygen atoms are in the same plane, and they form a Kagome lattice. This material is actually earthly abundant in clays and minerals. So for example, we take some clay as an example. The top layer or bottom layer automatically have this kind of monolayer Kagome silicates. And these kind of structures are literally everywhere in a lot of like minerals, clays, or soils. The other thing is this Kagome lattice have the well-known Kagome bands. Basically, you have 2 bands crossing with each other form a Dirac comb, and also a flat band that cap this Dirac comb in the bottom or on top of it. And we know this physics of the Kagome lattice because there are a lot of 2D models for this. So basically, we can use these systems to study the Kagome bands, which is automatically satisfied. The other thing is this monolayer Kagome silicates have already been synthesized under various conditions for more than 20 years. And recently, there are also a lot of proposals saying we can use different conditions, different substrate to grow monolayer silicates, or its like bilayer counterparts, which is a bilayer silica. Basically, it's another structure but protected by the mirror symmetry with the same lattice. So now we can directly look into the Phonon bands of the system. After we calculate the Phonon dispersion, we can immediately identify three groups of the Kagome bands. The first, the lowest one, is formed by the Phonon bands 10 to 12, and there are 3 bands between the 18 to 22 terahertz. And this band has a well-known feature of Kagome lattice. They have the Dirac cone here and a flat band that can be kept on top of this Dirac cone. And the second group have 4 bands, and they are formed by bands 13 to 16. And there are 2 flat bands that have this Dirac cone on top and on bottom and below this Dirac cone. And there are also a higher band, also have this 3-band system. The thing is, how can we induce the braiding process? Intuitively, we can just induce band inversion, similar to the case of single gap topology. For example, we can just use external electric field or some biaxial string to induce this band inversion. We'll first think about this external electric field. We can see in group 1, under an electric field of 0, this band gap between gap 10 is kind of far away from each other at gamma point. But if we increase the electric field, you can see like the band 12 and band 11 become lower, while the band 10 become higher. So we may induce band inversion if we can have some larger electric field. The other approach is based on the biaxial string. For example, we have these 2 groups of bands in group 2 and group 3. And basically, we can see even at a moderate string of 5%, these 2 bands are kind of touch with each other. So we have 2 ways to play with this band inversion and possibly the accompanied band braiding process. And I would like to mention that we choose the electric field on top of the string. So we fix the string and then we're playing with the electric field because it's an easy way. It's an easy way to do this because this 2D material needs substrate to support it. And we can use substrate to control these string conditions. And then we induce electric field to play with this non-abelian braiding process. We'll first start from the Kagome band in group 1. So we first think about the 7% string monolayer silicates. This kind of string is not very, it's very large for 3D system, but for 2D system, they are highly stretchable. And this Kagome silicates is also highly expansible. And experimentally, there are a lot of evidence in at least like 5% string is very feasible. So we can first start from a 7% string. And we can see upon an electric field, the band 10 at the gamma point with the 1D erupts of gamma 1 will move upwards, while the band 12 and band 11 with 2D erupts of gamma 5 will move down. So we can induce certain band braiding process by inverting this band. And before we do this, we calculate the topological configuration of the system. We know that there are only 2 band crossing points. The first is the K point, and with the 2D erupts of K3. The other is the gamma 5, also with the 2D erupts. That gave us a huge, and we use different symbols to denote this band crossing point at different gaps. So for the 11th gap, we use a triangle, and for the 10th gap, we use a circle. And the large triangle means that it's a quadratic dispersion, while the small circle means it's a linear dispersion at the K points. And we also use the field or openness of this circle to denote the sign of the frame charge. So in this case, we have like minus Q or Q in different K points. this is a topological configuration in our case. Now we say now we can just do some calculations and just find this band crossing point in the Abelian zone to see how this braiding process happens in the momentum space. In the beginning, there are just two nodes, but upon the band inversion, we can see three different changes. The first is this gamma 1 is inverted with this gamma 5 at the high symmetry line of K gamma. And so that immediately creates a band crossing point because these two bands have two different irreducible representation of lambda 1 and lambda 2. So they can move from the gamma point. So this kind of band crossing point will move from gamma point to K point with increasing electric field as the band inversion becomes stronger. And the other feature is this triangle now become a circle because these band crossing points are inverted. So it's similar. So basically, we have an effect of transferring the topological configuration from the gap 11 to gap 10. So the triangle now become a circle at the gamma point. The other thing is we now have another band crossing point because at the gamma m direction, because they also have two different Europe's of sigma 1 and sigma 2. And this triangle will also move from gamma to m. So basically we now have two nodes and also a topological, some kind of topological charge transfer between the two gaps. And these two, and if we let this, and if we further increase the electric field, this yellow point will move to the K point until they just merge at the K point when the electric fields are very large. And this also leads to certain like topological configuration change. And now the K points become a quadratic dispersion rather than the linear dispersion here. So this is basically the braiding process of the group 1. And so how do we determine these topological configurations? The thing is we can calculate the topological invariant based on the Euler class. For example, we'll take these two examples as an example. First, we can calculate the Euler patch around, for example, around two band crossing points. And if the Euler class is 0, that means they have opposite charge. And if the Euler class is 1 or 1, that either means they have a linear dispersion or quadratic dispersion, or they can have some like they have the same frame charge. That means they will not be annihilated with each other. So we can calculate the patch Euler class and assign the topological charge. So to get this topological configuration with openness, with open and filled circle to denote different sign of these systems. Similarly, we can also do the patch Euler class for all the bands. And after all this, and the calculations are actually very tedious because we need all these Phonon eigenvectors and then get these Phonon eigenvectors to do the Wilson loop calculation to get this patch Euler class in this patch of the momentum space. And after we obtain all this Euler patch, we can just assign this topological charge in different nodes and to understand the braiding process. So basically, we first get the nodes in the Abelian zone, then we calculate the Euler patch, and then we understand how this braiding process happens. And this gives us the non-Abelian braiding of the bands in group 1. So for example, if we just decrease the electric field from 0.7 to 0.0, these two nodes will cross with these two yellow nodes will just across the direct string of these nodes in gap 11. So their sign will be changed. So we will have 6 open circles. And in the meantime, the open circle of the triangle, the sign triangle, will also be changed because it's also crossed the direct string. So now we have 6 open circle and 6 closed triangles, and they can be recombined with each other and form a large triangle here, which means they have a linear quadratic dispersion at the gamma points after all these nodes are recombined with each other. So this is the braiding process, and we can only like unbraid this process by reverse this electric field. Now we understand the braiding of bands in group 1. So the question is, are there any other braiding process in these configurations? So at least, so we can now analyze the braiding between group 2 and group 3. We can see it like with increasing electric field, these bands 16 and 17 also go down, and the band 16 group 2 is moved down forward slower than the 17. So we can also get this band inversion around gap 16, and they'll first start from the from the K points. And at about 0.1 electron EV per astron, we can see like this blue circle will just bounce from the K point, will be created near the K points and move to gamma points. And after these two bands with gamma 5 and gamma 6, they will be inverted at further electric fields. So we can, so this sign will also be changed. For example, the yellow circle will just be bounced back, and their topological frame charge will also be changed. The sign of this frame charge will also be changed. So originally, these two nodes can be annihilated with each other. However, if we invert this process, if they bounce back from the gamma point, they have the same frame charge and they cannot be annihilated with each other. We also have some other like nodes because these different irreducible representations of the system. So we also have these yellow nodes at gap 15 and also the square nodes at gap 17, and they'll also move from the gamma point to M point or to K points. So basically, we also have a new braiding process involving more than 3 bands. And this is the first materialization of non-abelian braiding of more than 3 bands in this case. Some open question of our project is about boundary correspondence of multi-gap topology systems, because we know that these topological phonons will have the edge states. And if we calculate the edge state of 100, we can see like there's a surface arc, edge arc that connecting this band crossing point at the gamma point. And if we do the calculation for all these electric fields, we can see like at some point we can also get some new surface states as the band is inverted and there are more band crossing points here. And similar effect can also be found in this braiding of 2 groups of bands. So for the K points, it's a stable edge arc that connecting connecting the nodes at the K points. Whereas for other Ks, we can also have other topological edge states, and these edge states can also be involved at different electric fields. Because this band inversion create different nodes as a result of different errors. In the last, we want to show that there are some experimental signatures based on the Raman spectrum of the system. For example, if we consider the first braiding process, all these braidings are at the gamma point. So as long as the band inversion at the gamma point can be detected by the Raman peak, and all our braiding process, all these nodes are actually Raman active, which means we can use Raman spectrum to detect this band inversion process. So originally without any electric field, we can have a strong peak at the high phonon frequency and a weak peak at the lower frequency. And as we increase the electric field, we can see the high frequency peak with the large intensity becomes lower as it moves lower, while as this lower intensity bands, low frequency mode will move upward. So we can observe this band inversion process by Raman signature. And similarly, for this braiding of the braiding of the 4 bands in the 2 groups, there are also these two Raman modes can be inverted with each other. So we can see like two different peaks with different intensity will change their position, and the braiding process can just be observed by the Raman spectrum. Some open question, some outlook of our project is, can we find some new material candidates? Because these layer silicates are literally everywhere and with a lot of different structures, different phases. The other thing is these Kagome lattice are also everywhere as long as we can have some tetrahedral like some other in other materials. So we recently working on other material candidates also in monolayer systems because 2D physical model, 2D Kagome lattice is well understood. And the other outlook is, can we also realize the braiding between no rings and no lines? Because we only focus on the braiding of nodes. And if we also have no rings or no lines, they also carry this barrier phase of pi around these nodes. So this may also be some new braiding process. Some further outlook may be can we realize some topological qubits based on phonons to encode this quantum information in different phonon nodes? And also, can we develop some like algorithm of these topological qubits based on phonons? But these are all open questions. In our work, we just show like we can realize the non-Abelian braiding in momentum space of phonons in this layer silicates. And we propose an experimentally feasible way of Raman spectrum to understand this layer silicate. And the outlook is, can we realize this topological quantum computer based on phonons? And you can check our papers in arXiv. And with this, I would like to thank my collaborators, Asian, Tamil, and Robert. And thank you for listening.